Morning, friends. Today I named the session as The Great Escape. This is not a game. I'll be talking on a concept using based on random walk on plane. So here is my two-dimensional plane. The coin's origin here on the pink spots, and then traverse the plane across x-axis and y-axis. So so the coin is here now. Now I am moving it. The probabilities in every direction is zero point 0.1. So that's zero point 0.8, and probability of staying in the same position is zero point 0.2. So these are the transition probabilities to different directions. All the probabilities are zero point 0.1. This is not simple random walk. Simple random walk only gave probabilities to move on x-axis and y-axis, but here I have considered the corners also. So let me move the coin. So it is moving now. So I have given this probability as 0.2. So let me set it 1 first. I'll set this probability as 1 and refresh the screen. So the probability of staying inside this green box is 1. It won't escape the green box. So it starts from the pink circles and then traverse the entire collection of green circles. This is called a random walk. And for a random walk in two dimension and one dimension, the probability of eventual return is 1. So you start from anywhere and then almost surely you are coming there back. But in higher dimensions, starting from 3, 4, etc., the probability is not 1. So you may lost in the space, but in one dimension and two dimension, you don't get lost in the space. You come back to the origin. So that is the experiment I'm going to do, whether it comes back to the origin, but it takes time. So I have given some constraints. So this is the way a coin moves around the xy plane, the Euclidean plane. So if I give two heads or two coins, I'll number this as 2 number of heads. It can vary from 1 to 4. So now there are two coins and they move around. The minimum distance, this is the Manhattan distance. So distance between two coins is 1, 2, 3, 4. So distance between them is 4. So that's the maximum distance. Max distance is 4 and the minimum distance is 1. There are some fun. If I bring down this minimum distance as 0, I'll talk about it. But this is the way two coins move around the plane. Now they are not going out of the green circles because I have given the probability as 1 to stay inside the green circle. This is random walk of two coins. Now I'll change the mean distance to 0. This is playground size. The playground size is 3 now. On the right side you can go 3 circles. On the left side you can go 3 circles. In top and down there are 3 circles. So the playground size is 3. That also can be changed to any number bigger than equal to 0. So I'm going to the minimum distance. Minimum distance, if I put 0, then two coins may coincide and they may become 1, and the number of coins become 1. So that option is also there. So it's a symmetric random walk, but not the simple one. The two coins are moving. Maximum distance is 4, minimum distance is 0. So they may coincide. Now it has become 1 because they have coincided. So to avoid this, I put the minimum distance as 1. I put the minimum distance as 1. And I reduce this probability. Now I'll be allowing the coins to move outside the playground, outside the green dots. They can go out to the space. So I'll be seeing whether they are coming back or not. So that's the experiment. 2 8s, minimum distance 1, probability. I have to change the, I'll reduce the probability to 0.2. Probability of being inside the original room is 0.2. Here also the probability I will make 0.2. Now I start the process. This 0 denotes the displacement of this pink original room. So now the distance is 0. I allow the distance to be maximum of 10. Then it comes back. So it's not a pure random walk. I have put some constraint that the original room can move only 10 distance, only a distance of 10. Maximum the distance can be 10. Now the coins are doing a random walk. Now the room has started moving. Now that the coins are drifting apart, I'm keeping the coins on the screen so relatively the playground and the origin room is moving. The distance is 6 here, it can go up to maximum of 10. Let me see how does it behave. It's all random. Here I count the number of clicks. Till now I have clicked 50 times. The distance is 6, it can go to 10 at the max. The maximum number of clicks I can make is 1000. So when it crosses 999 number of clicks, everything resets to 0. I can accommodate a maximum number of 4 coins. It's all happening based on the random numbers. Now the distance of the origin is 9. It can go up to 10. Now it is 10. Now it will come down. And let me see if it comes down to 0 or not. Now the color has turned to light brown and the maximum distance is attained, that is 10. Now it will come down to 0. But I don't know when. I may not be able to complete the process. If it takes more than 999 steps, the process won't complete. The coin needs to move to top right corner to reduce the distance. The distance is remaining at 10. Number of clicks is 1208. Now the distance has come down to 8. Now it is 7. The playground and the origin room is coming back. The distance is 6 now. The coins are doing a random walk on plane. They were inside the playground with probability 1 at the beginning, but then I reduced the probability 1 to zero point 0.2, the probability 0.2, so that it has escaped. But I have a control over the distance of the origin room, and that at the max can be 10. So now it is coming down. It is 6 now, 5. It's fun to watch the movements of the lifelike coins, right? Two coins are moving freely on the plane under some probability, under some with some probability to with some transition probabilities, which are 0.1 in every direction, and the probability of stay is 0.2. So the total probability is 1. Distance is 0.5. Distance is 5 now. I have done 335 clicks. At the max, it can be 999. Now the distance is 4. Now the distance is 2. So eventually the distance will come down to 0. It's only a matter of time. The peak circles need to move only 2 more steps to the left and the distance will be 0. But since the coins are having a free movement in the plane, I don't know the stop time when this is going to happen. So one has to wait only. I'll I'll continue till click 500, then I'll stop because I think the concept is clear that in two-dimensional random walk to two-dimensional random walk, the probability of eventual return is 1. So we just need to wait till the random point comes back to its original position. The probability 1, but the distribution of the stop time I don't know when it is going to happen, when the eventual return is going to happen, that I am not sure of. That's called the stop time. That has a distribution. 479, 480, 490, 492, 493. I'll wait till 500. 98, 99. Okay, I'll stop here. I hope you enjoyed the video. Thank you. Bye.